Thanks so much for waiting, and welcome to this talk on multi-model powered machine learning. A quick raise of hands, who knows what multi-model is about? Oh, that's actually more hands than I expected. But we're going to clean that up during the talk and kind of explain what it's about. In short, so kind of the short summary is, how can we combine especially NoSQL databases and machine learning? So how can they be useful in the machine learning lifecycle? And we're going to dive into kind of like two subtopics. The first one is, how is it actually helpful in terms of analysis itself or feature engineering? So basically being part of the core machine learning pipeline. And the second one is actually about how is it useful from like an operational perspective if I actually need like audit trails or meta information about my machine learning pipeline. Maybe a quick raise of hands, who have used like a data scientist? Who have used a data engineer or operates machine learning pipelines? Okay, so probably the first one is more oriented towards data scientists, second more towards data engineers, but in my opinion actually both is very important for both kind of personalities. This is actually all covered under a project initiative called Arango ML, but we'll also learn about that during this talk. I'm Jorg, I'm the head of engineering and machine learning over at ArangoDB. Previously to that, I've always been switching back and forth between database systems. So my PhD was database systems, and I was over at SAP for HANA. Then I switched over to large-scale infrastructure, where I built a lot of machine learning systems. So I actually really like that talk, because it kind of combines my two passions for those two fields here. All right, maybe just a quick reminder, machine learning is kind of the new hype topic nowadays. This is also why probably this is the AI theater. And clicking works great. And so what do we usually imagine under machine learning? We imagine like a data scientist sitting there using TensorFlow to write like really cool stuff. And so actually becoming the superhero, which nowadays, given the large amounts of data we have, the large amount of computing resources, and also the recent advances in like machine learning algorithms, can actually really shine as a superhero, build cool stuff such as self-driving cars, and be like really cool. So unfortunately, this kind of naive assumption, which is like data scientist is sitting there, he's getting a data set, he's developing this cool model, self-driving cars on the road, so training a model, running a model, and then actually he can start the next problem. That's a bit very naive, because in reality, the kind of time distribution looks very differently. So this is even from a Google paper. So those guys are pretty advanced if it comes to that. And this writing of ML code is actually just a small black box here in the middle. Everything around is actually feature engineering, cleaning up data sets, or managing infrastructure here. So this is probably like one of the core challenges we are facing here. And this is also why TensorFlow, or your favorite machine learning frameworks such as Pytorch, MXNet or so, this is mostly focused on this, maybe a little bit here on like those parts as well. But this is also why we need other tools in our tool chain. So if we look at a typical machine learning pipeline, it always varies a bit who you're talking to or what you're building. You typically have those stages roughly. You have your data, which you need to manage. This can either be streaming data, this can be data at rest, being stored in HDFS, being stored in a more structured form in a database. Then we have feature engineering. So feature engineering is when a data scientist comes in, he's cleaning up the data set, he's extracting more rich features from that, so basically cleaning the data, trying to already do some analysis. And this is then being fed to a machine learning framework. This can either be deep learning, this can be other machine learning tools, but this is actually the part where then TensorFlow, Spark, MXNet, Pytorch are coming into the picture. After we have actually built our model, and keep in mind, typically we are not just building one model from a data set, but we're actually building a bunch of different models with different hyperparameters. Maybe we are even updating the data set, so we need to retrain. So actually, even for one problem, we end up with a large number of models we need to manage, and then actually decide which ones we want to use for serving, i.e. using it for like our production data set. So in this machine learning pipeline, we have like nowadays it's finally coming up that we actually have some open source implementations for those. The two most well-known ones are probably TensorFlow Extended, which is based around the TensorFlow ecosystem. And you can already see this pretty much matches to what we've talked about before. You got data on the one hand, you got data cleaning on as a second stage. Here we got our model training, model analysis, pushing and model management, and then actually the serving at the end. The other one, which is also pretty well known, is called Kubeflow pipelines. So Kubeflow originally was a project for TensorFlow on Kubernetes, and now it actually has evolved into kind of its own ecosystem around machine learning on top of Kubernetes. So they're actually related, and they also talk a lot to each other, those two communities, but those are probably like the two best known pipelines for machine learning nowadays. All right. As promised, we want to bring databases into this picture. I guess the kind of obvious part where we would expect databases is here on the left side for data storage and data streaming. Databases seem kind of like a perfect natural fit for that. The second part where it becomes more interesting is this feature engineering part, where we already start utilizing our database for extracting value out of our data, so kind of the processing part. And just to have a motivating example, this is actually a Wikipedia movie plot. So the data contained in here, it's basically a data set on Kaggle. Kaggle is a platform if you want to compete in machine learning competitions. This is probably the platform to go to. And so we have here data, release date, title, what is the origin of that, who is the director or directors, who is in the cast, what is the genre, and then also like a full text plot description. And given that, we can start asking pretty interesting questions. So first of all, for example, recommendations. I have some favorite movies, and now I want to figure out which movies are different and what can I watch actually tonight on the couch because it's raining outside. Also classifications, like if I don't have a genre for a particular movie, or I'm trying to come up with a new movie, how can I actually classify the genre maybe automatically? How can I find a movie based on the plot description? I have a bunch of friends who come over and they're like, hey, do you know the title for this movie? And then they start explaining the plot. Wouldn't it be cool if we could actually just predict that using machine learning? Or even if we are a director, we know we want to have a movie in like the horror genre with Batman or something, that we actually automatically generate a plot like generative machine learning. So actually we have a lot of different uses where we can apply machine learning to this data set. And now let's kind of loop over to graphs. So this is still like a very structured format, but graphs are actually becoming very popular as well for machine learning. And in my opinion, this is given the fact that we as humans, we often think in actually graphs. Even we are not aware of it, we often think about like different entities and their connection, their relation to each other. And this is actually why we, for example, can also here, this can actually be easily turned into a graph, as we'll see in a second, where, for example, director is like one word, one like node in the graph, and then we have a connection to all the movies he has made. So this is basically this connection over to a graph, and this is actually how we think. If we think about a certain director, probably it comes to mind what movies has this guy made, or woman. So if we kind of turn over our data set here on the left from the tabular form into a graph, this, as mentioned, corresponds a lot to the way we're thinking about how things are working in real life. So for example, here we got some movie titles. We have an edge with certain meta information like directed by. So we know this movie has been directed by this director. This person played in that movie, and so on and so on. Here's the origin, kind of it's an American movie, and we can actually express a lot of this information in graph form. And this also allows more natural ways of querying that data. So basically we can have graph traversals finding similarity, we can have graph traversals of finding like everything which has been made by one director, whereas formulating a lot of that as SQL queries across a relational database becomes really, really challenging. So the first thing we can easily do is, for example, extracting certain feature using graph analytics. So a very simple question is, for example, just finding out, like, for all directors, how many movies they have made. This is still something we can easily express also in SQL if we are looking at the relation here. But we can also have more complete queries, like find all the movies which are similar based on the set of actors who have played in them. And then it already becomes very, very complex to express it in SQL, whereas in a graph, we basically just look at the graph connections to another movie here. Second feature, so as mentioned, we want to talk about multi-model. So we already talked about graphs so far. Let's talk a little bit about other ways to query data or to look at data. So graph is one data model. Another data model is, for example, key value. Yet another data model is our documents. And then secondly, there's also the way in which I can process them. So many of you probably know Elasticsearch, and that's kind of like a full text search engine. And with that, I can have questions like find all the movies which have like Batman and Robin somewhere in their plot, or even more complex full text queries, and leverage that. And then I basically get a list of movies where either Batman or Robin or both of them are appearing in the plot description. And this idea of multi-model, that basically like one data model isn't sufficient to answer all queries, this is one of the core ideas of ArangoDB. You probably have heard of like a sole graph database, a sole document database like Neo4j, Mongo, and what in real world, what we've seen over and over again, is actually that one data model isn't sufficient to represent all different kinds of use cases. So the idea is actually that ArangoDB can handle all those data models naturally, and actually provides also all the query capabilities, such as graph traversals, such as full text search, such as joins, such as like document queries across those different data models. It's distributed, it can run across a large number of nodes, and also has a certain support for ACID transactions. I think I covered that already sufficiently. I don't want to dwell too much on product decisions here. So basically, what it comes down to, if we talk about feature engineering, is we take our raw data set, we can leverage a graph or multi-model database to extract like core features, which can then be handled by something like TensorFlow for deep learning, for example, or for other machine learning techniques. What is kind of next in that field? A really interesting advancement is that we are also talking about graph neural networks. So basically imagine a neural network which can leverage graphs directly. So this is a really interesting future direction, and we are, for example, supporting already certain node embeddings directly from ArangoDB to allow this kind of movement. All right. So we talked about data and streaming, we talked about feature engineering, but kind of probably the most overlooked fact is that databases are also important to actually run this entire pipeline efficiently. So one of the challenges I've been seeing in the past when building machine learning pipelines for finance, for healthcare, was that we actually had to figure out like, hey, we had this data set with certain patient records, and we wanted to figure out like which models currently running in production are impacted by that. The use case was that actually that patient had said he did revoke his right for us to utilize his data. Under GDPR, it's a bit unclear whether that's impacting the models or not, so there's a bit of discussion around that. But at least we wanted to be able to identify all the models which kind of had been impacted by this one data set with this one patient record there. And given our machine learning pipeline, this actually turned out to be pretty hard, because the metadata, where's the data set stored, which data set was used for which feature, which features were used for which model training, which model ended up in model management, and which model was being served here. This actually ended up in different systems and different metadata stores. And so we actually had a hard time answering this question or other questions, as for example audit trails. Where is this model being derived from, making this decision to deny your credit application? finding model differences in performance. Imagine we have two models being trained by the same data set. We simply want to figure out the training difference, the training accuracy differences, and also figuring out from data scientists, if I tell a data scientist, please, I need a better version of this model, which are actually the intermediate steps which he can reuse, which Jupyter notebooks he can reuse, which data sets are in there, and so on. So basically just get also a full picture of that pipeline. And we had a pretty hard time answering all those questions. And this is actually why we came up writing a common metadata layer. So basically one database collecting all the metadata across the entire pipeline. And metadata in this way is referring to, for example, different things. So at its core, the definition is basically a description of all the entities which are used in my machine learning pipeline. So this starts up by the data set. It doesn't contain the data set itself, but it contains a description of the metadata for a data set. Where is it stored? How large is it? When was it created? When was it updated? And so on. It can contain transformations. So how do I transform my data set into certain features? That might be a reference to a Spark job, that might be a reference to a TF transform function, but basically the kind of connection between a data set and a certain feature. Then similarly as data sets, I actually have versioned features, which I also need to keep track of. So which features do I have? Where were they used for? When were they trained? Do I maybe even have like a newer data set and I should retrain that? Other entities are Jupyter notebooks or also other notebooks which are around, like Zeppelin, where the data scientists have worked on and actually exploring that data set and developing a certain model. Then inside I can have a separate model function. Very important metadata is around experiments, where I really care about train and test performance. Also, for example, was really important later for accounting for us was how many resources were used by experiments. So if I have a model somewhere running, it was an important question for us just from an accounting perspective. How much did we spend on cloud resources? How much did we pay for Amazon training this one model? And then obviously we have models, and also in serving, we also collect a lot of metadata as serving performance. If we are, for example, predicting click-through rates, this is something I can pretty much directly get and also store as metadata. So there's actually a lot of metadata across that. And the next question we had to ask ourselves was, how can we actually store that? And this is where we actually came back to the idea of multi-model, and this is why we then actually developed Arango ML pipeline, which is like an extensible metadata layer, and we'll see it in just a second what that actually means. But basically we came over to ArangoDB and developed our solution, Arango ML pipeline, based on that. Why? Again, this is a really good combination where I have different data models. On the one hand, if I, for example, want to describe my model performance, my training performance, this really nicely fits in a document with different formats. Training performance, test performance, how long did it run, on which infrastructure did it run. That's basically like a JSON document we can imagine. And the challenge is, it's not the same between all different machine learning frameworks. So I get different outputs if I use, for example, MXNet than I would do from TensorFlow. And this is why it was hard for us to fit that in a fixed format, and we were really happy with like a document format. Similarly with like data set descriptions and basically the metadata for all of that all fits really nicely in like a document form and a document store. But on the other hand, we kind of need the connections in between. We need to know like this experiment was run with those features, this feature was being formed by those transformations from those data sets, and so on and so on. So we actually wanted to form some kind of graph across all of that. And this is then where kind of the idea of multi-model becomes powerful, because I can combine two data formats, two data models being supported here, the document one and the graph one, and then queries such as like which data set is impacting which models. It simply becomes a graph traversal, a graph reachability question. And if you look at that, also keep in mind like a feature might actually be derived from another feature, or a model might be derived from another model if we do transfer learning. So it's not like just a simple like straight join we could do across all those entities. It actually can also have loops across all those entities. But formulating that as a graph tree, it was actually very simple. Of course, we can basically just say like, give me all the models which are reachable from this like one data set, or in this case from this one feature set, and just traverse the graph. We actually have in Arango ML, we don't have a fixed schema. We have certain entities which are being supported out of box, pretty much the ones we saw earlier. But the nice thing about, as this is just a document, we can actually create new ones. So if any machine learning pipeline is coming up with different entities they need to support, they basically just add like a new entity here and they add a new edge. Similarly, I can also remove stuff. So I can, for example, also just have an edge between experiment and notebook if I don't want to store the model function separately. And this really made it for us very flexible and very extensible, because I wasn't tied into like a specific schema for my overall machine learning pipeline, which differs quite massively between different organizations I've seen in the past. All right. So what else do we have in here? So we can discover. So we have a UI, and this, for example, allows a data scientist to discover like all the entities which are related to a deployment. So I want to find all the models here which are in this deployment, which might be running somewhere in our cloud, somewhere in our infrastructure, and similarly with other things. Furthermore, I can actually explore the graph representation of that. So once I've found my deployment here, I can actually see everything which is related to that, like serving performance, dev performance, different model parameters, and so on. And I can also just explore that as a graph view. And this comes back to kind of like how we work as humans. This is actually very easy for us to comprehend, as opposed to if I had to write like a SQL join to actually jump through my entire data set. So we as humans just have a very natural way of dealing with graphs, at least from my experience. Feel free to disagree with me there. From an API perspective, we're integrated into this TensorFlow ecosystem natively, because they actually also came up with an interface for that. So if you're running TensorFlow extended, you don't have to do anything to store your metadata in there. For the other things, we actually got Python packages and HTTP APIs, which make it easy to store your metadata in there, and then also query them either using ArangoDB directly, so you can just formulate any AQL query, or also leveraging those APIs. It is all open source, so it's all here on GitHub for everyone to try out. And I actually even wanted to give a demo, as I had to switch to this laptop. Unfortunately, I can't give that demo, but I'll give you a short rundown of what's happening there. It's actually pretty much what we just described about this knowledge graph. And the good thing is it's all open source. There's a Jupyter notebook you can simply run, and I'll also share the slides later on, and you can just run through that. So it's basically this entire pipeline, starting from the feature analysis, using full text search, using graph, feeding it into TensorFlow, and then also collecting the metadata for that in Arango ML. And so this basically gives you this entire rundown of how databases are useful in a machine learning pipeline, in a machine learning system. So I think I'm like five minutes short, so we have some time for questions, but that was basically planned for the demo. So otherwise, everything is also online. I'll also put the slides online. So there's Arango ML, which basically is the machine learning part, and then there's ArangoDB here, and also the demo. Both of them are online, and feel free to dive into there. Thank you so much for listening. I think now we have like still 4 minutes for questions left.